Hello, everybody. My name is Adrian Duque, and I'm actually responsible for the eMobility business of Schneider Electric for the Asia Pacific region. So it's really a pleasure to be part of this event, and my presentation will actually focus on smart charging for buildings. So to start off, I'd like to briefly point out the three global e-mobility trends that are shaping our world at the moment. First one is sustainability. So this is very critical, not only for humanity, but also for the planet and of course our health. So we've seen that there were pledges from 195 countries to limit global warming to 1.5 degrees above pre-industrial levels. So this is a key driver for the electrification of our transports. And also we've got the European Green Deal, which actually set a goal of zero carbon emissions by 2050, and with a middle objective of reducing emissions by 55%, excuse me, by 2030. So because of some of these commitments, governments are actually moving and regulating in favor of e-mobility, which brings us to the second trend. Governments are moving to a net zero mobility. As an example, banning of internal combustion engine vehicles in different parts of the world. From now on, maybe from 2020 up to 2025 or to 2030. Just some examples is that, like in Norway, ICE vehicles will be banned by 2025. In UK and Denmark, 2030. In California by 2035, and in France by 2040. So we've also seen movements from China, which is probably the biggest market for electric vehicles, with the zero emissions vehicle mandate. This basically stipulates that each Chinese vehicle manufacturer and importer is required to make or import at least 10% electric vehicles. So the percentage actually increases year by year. So the other drivers of adoptions include city access restrictions for ICE vehicles, and even financial incentive to buy eco cars, and some economic stimulus through recovery plans, including the EV infrastructure. So all of this is causing for the third trend, which is the new energy landscape, to spread faster than expected. So we're talking about renewables here, environmental, social, and governance investments in the low carbon energy transition. It's actually increasing, especially in renewables and the electrical transport as main drivers. So due to the three global trends, EV prices are actually dropping and the adoption is accelerating. According to some experts, it is forecasted that price parity with conventional vehicles will happen before 2025. And by 2030, it is expected that 30% of global passenger vehicles will be fully electric. So as a point of proof, actually, if you look at this slide, battery electric vehicles and plug-in hybrid electric vehicles has increased by 108% last year. So with China leading the way at 155% growth, 66% for Europe and 96% for North America. And we see that by 2025, we can expect exponential growth. Um, One behavioral change will be the way what we call fill up our vehicles when we're talking about gas or petrol vehicles. Traditionally, with ICE vehicles, we stop at a petrol or gas station to fill up. For EVs, it's going to be different. It's basically we charge or fill up when we stop. So with the development of batteries, the range is actually increasing, and this reduces the need to charge in transit. And in terms of cost, charging EVs at homes or in buildings is actually more cost effective for drivers, as they can take advantage of maybe time of use tariffs, solar generation, and even demand charges. And in terms of convenience, based on studies, charging at home is actually preferred by most drivers. So in saying that, as such, homes and buildings are actually at the center of charging ecosystem. it is estimated that around 90% of EV chargers will be installed in buildings and homes. So this is me saying that building owners need to be prepared that the infrastructure for an increase of up to 45% in electricity consumption due to the charging needs. So EV adoption is actually skyrocketing. About 16 million EVs were on the road by the end of 2021. And IEA estimates that this will grow to about 145 million by 2030. So we know that EVs have a starring role actually in a clean energy future, but they need to be supported by a robust smart charging system. So the rapid shift from gas-powered vehicles to electric is actually a central piece for many countries in terms of their sustainability plans, because 100% electric mobility is an efficient, sustainable way to reach net zero. So to keep pace with the EV adoption, the world needs exponentially more chargers, both public and private, to meet the changing charging behavior. So, however, uh, challenges, buildings, electrical distribution systems, they're actually not designed to handle the large energy loads needed for the additional chargers. This is especially true for the existing buildings. It will add complexity to the grids and push buildings' existing power distribution networks beyond their capacity. At the same time, adding the risks of overloading the building's electrical network and triggering an outage. So these challenges can actually be addressed by a smart charging system, as it will reliably meet the increasing power demand from EVs in buildings. So basically, to define what is smart charging, so we define this as a system that can monitor, manage, and eventually regulate the use of EV charging devices with the aim of optimizing energy consumption. So you can see the adjective smart there. It underlines how this solution is able to intelligently and flexibly adapt the charging strategy to meet both the EV users, and the power grid. It also allows flexibility, optimized energy consumption, infrastructure scalability, and of course, cost efficiency. So buildings need a smart charging infrastructure as it ensures power availability by minimizing the EV charger infrastructure's impact on the existing power distribution system. So smart charging and digitization technologies, the word digitization is quite important there, are used to create a better, more efficient smart charging experience that it makes it easier to actually integrate renewable energy and provide resilient power. So in a scenario where we've got different EV charging scenarios. So one of them is like a scenario where there is no there's just no load management setup. So which means all EVs are plugged in and will simultaneously begin to charge us at maximum power, meaning there is no control. So the energy being used for EV charging, in addition to the normal building loads, could result in overload and potentially exceed the maximum capacity of the building. So the upper limit in the total electric demand that can be placed on the network will be exceeded. So to avoid this scenario, most EV charging setups have adopted some standard load management practices. So the next scenario would be having load management. So load management can be static or dynamic. So this refers to the level of set point that you put in. It can be static or it can be dynamic, in which is there is a defined threshold. So only the remaining power available for EV charging is distributed among the connected EVs with priority to the normal load of the building. So EVs can also be charged at predefined times to optimize off-peak and electricity tariffs. So these standard load management practices draw on a reactive logic, which does not forecast today's building needs or anticipate specific needs of EV drivers, like when do they leave, when do they arrive, how long will they be charging. So the growing adoption of EVs is increasing the impact on the existing power distribution system. So providing scope to further optimize our EV charging infrastructure. And when we're talking about smart charging, so this is the last scenario, smart charging is more advanced than a classic load management setup. So it is intelligent. It's a system that provides proactive logic, so for scheduling and ensuring an optimal charging solutions. So in this case, each EV is actually plugged into the charging stations with a specific charging schedule. It not only takes into account the EV drivers or the fleet needs, example like departure time, but also respects the power limits of the entire installation. So this ensures that we don't go over the maximum capacity of the building. So a smart charging system also provides the infrastructure owner with a significant OPEX savings by optimizing the use of locally generated renewable energies if it is present, like maybe a PV or wind, and using dynamic electricity tariffs for cost-effective charging. So to demonstrate that, we've got a case study here where a company X wants to allow its employees to charge their EVs. So you can see there's a schedule on the right on when they arrive, when they leave, how much power they would require. So there are 9 EVs there, and you can see the different times there. So a smart charging system creates a dedicated charging profile for each EV. And it's taking into account two things. First, the EV needs, departure time, energy requirement, number of kilometers to go are asked as inputs for the EV drivers. The second one would be energy constraints on the building ecosystem. So this is to optimize the operational cost. So there are actually four possible scenarios that will result in this. As you can see on the right, we got four scenarios there. So I'll be talking about them one by one. The first one would be a scenario where charging without solar generation and you've got a flat rate for your tariff. So the thing here is that EVs do not start charging immediately. So maximum, as you can see there on the second point, maximum power is assigned to the EV number 2 and 7 initially, taking into account the EV's time of departure. So if you remember, if you could see from the previous slide, um, the EV2 and 7, they're leaving quite early at 11 a.m. So that's why they're giving priority in terms of charging, as you can see here. And also the maximum power limit threshold is also taken into account at all times. So during charging, so as not to overload the power network. As you can see here, once at around 11 o'clock, EV2 and 7 has left, stopped charging. As you can see, they're not included in the other parts of the charging sequence. Another scenario would be charging without solar generation, but the tariff is variable. So one thing to notice here is that the control algorithm starts charging EVs, but when the waits of the off-peak hours to finish the charging. So as you can see here, there's like a blank there because the tariff is quite high and it waits for tariff to go down and resumes the charging. So the system detects high tariff and therefore stops the charging for a couple of hours, as you can see there between noon and 2 p.m. Calculating that there is still enough time left for the remaining EVs to be charged the expected levels before their departure. So as you can see that the electricity tariff is at the minimum between 2 to 5 p.m. And so that's the charging is resumed between these hours. The third scenario would be charging with solar generation and having a flat rate tariff. So as you can see, there is quite easy to look into is that the charging curve is actually aligned with the PV production for maximum gains. And the last one is actually charging with solar generation and the tariff is variable. So a combination of both worlds that the charging curve is aligned with PV production and the operational cost is actually optimized by charging at off-peak hours at a lower tariff, as you can see from here. For this use case scenario, it was found that we discovered 25% savings in operating costs compared to the others, and compared to the standard load management system on operating costs. So, what are the benefits for doing smart charging? So, in terms of the stakeholders, when they were talking about building owners, it provides lower capital expenditure because smart charging, it does eliminate the need to oversize the EV charging infrastructure. So this provides the opportunity to downsize the transformers or even the switchboard that you have in the site. It also optimizes the entire building's energy use. So it optimizes the electrical system's overall capacity and infrastructure. It does raise the commercial value of the property too, because it attracts tenants with the smart EV charging stations. And you can actually monetize the charging stations that you have there by having it publicly accessed and make money out of it. And lastly, it actually complies with sustainability regulations if there are some. In terms of facility managers and fleet operators, it actually improves power safety since reliability without compromising the building's existing power demand or disrupting building occupants. So OPEX is also reduced, mainly because smart charging can use dynamic tariff or even use PV consumption if it is present. Optimization of power and structure maintenance as it's using operations data from the EV infrastructure, so you can make analytics there. It lowers the building's environmental impact since energy is being used more efficiently. It also accelerates the CO2 footprint reduction if you have those such goals, and it does increase EV driver satisfaction. And from a driver's perspective, it actually brings peace of mind as they know that when they park and they charge, they will have enough charge capacity when they leave. It also saves money because, as I mentioned earlier, charging at homes and in buildings is a more cost-effective alternative compared to charging in transit. And lastly, it benefits for more sustainable options, such as choosing only to charge with green energy. Okay. So smart charging actually will evolve. So as we see here, current technologies, we're looking at step one where you can only do basic control with the use of time of use tariffs or basic scheduling and maximum power. But eventually we will move to step two where you've got unidirectional control or what we call V1G, vehicle uh, one to grid, where EVs and electrical supply equipments or EV chargers, they can negotiate a charging profile based on various constraints and data points. Step three is bi-directional charging, but this is limited to vehicle to home or to the building, which we call V2H and V2B. And lastly, that's where we have interaction with the grid, where you've got bidirectional charging, vehicle to grid. So these technologies, even in step four, currently there's already some trials going on in multiple parts of the world. It's not mainstream yet because regulations have not been done. There are other things that needs to be considered in order to ensure that it's a safe application for charging. So we also have to address the challenges that lies ahead. So EV
Adrian, I'm
drive,
really sorry
yeah,
to interrupt, but if we can get to the wrap up, we're running out
okay,
of time. Thank you.
yeah, I've got two more slides actually. Okay,
Go
so the
ahead.
needs for EV drivers, we've got limited need the communication is limited, standards are needed there, and in terms of interoperability, this is where digitization comes in, where it needs to be interoperable with different open technologies or open communications, and of course, cybersecurity is needed there too, and tariff incentives, deployment roadmap, and regulations. So key takeaways, I guess, would be EV adoption is growing. 98% of EV chargers will be in commercial and industrial buildings. That's why it's quite important. Existing buildings were not built to have huge increase in energy demand, so they were designed to have EV chargers. So the only way to solve this is to have smart charging technology or infrastructure within the building.